Today's topic is absorption and dispersion, and the question we're addressing is what happens if we have an electromagnetic wave in a conductor. And in a conductor we have unbound charges. And these are going to move around as we insert an E field into the conductor, and this is going to change the wave equation a bit. And we recall that for an ohmic conductor we had that J is proportional to the E field with a constant sigma, which is called the conductivity. Okay, so now if I let's say send an electromagnetic wave onto a conductor or inside a conductor, that's an E field, which is going to introduce a current, which we didn't have in a dielectric, because then sigma is essentially 0. And then we have no conductivity, no currents. So we're going to assume that ohmic conductors for now, because this is the simplest case, and it's surprisingly general. Also, we're going to assume the following: that we have no sources. In the sources of D field, no charges. So you're not going to have any accumulation of charges. And if you're wondering about that, you can read in the book. There's a nice argument showing that if there's a charge accumulated in a conductor, it's going to dissipate because it's a conductor, and charges of the same sign are going to repel. And this is the reason why we can quite safely assume that there's no local charge, but there might be currents. So that's our assumptions, that we have currents but no charge, no lumps of charge lying around. Okay, and what we did previously was that we built polarization into the D field. And what I'm going to do now is to try to put also conductivity into the D field. And what we had before was that D is equal to epsilon naught E plus P. This is basically electrostatics, right? And so the time derivative of this, which appears in Ampere's law, is just the time derivative of each term. Like this. And this forms the right-hand side of, together with the current, this forms the right-hand side of Ampere's law. So we have and now RHS, of course, means right-hand side. So that is J plus dt epsilon naught E plus P. But if you go to the frequency domain, this is simpler, because now the time dependence on this is not a trivial thing. But if you go to the frequency domain, we take the Fourier transform, then we get the following. And that is that a frequency wave number domain. Let's see. And then we get that J as a function of wave number and frequency rather than time. And then minus I omega, because derivatives, when you take the Fourier transform, is just I omega multiplication. And then we have epsilon naught E of K and omega plus P of K omega. And then we say that, okay, this should be epsilon naught epsilon R of K and omega times E. So I basically put all the polarization into the dielectric function. That was the idea of introducing the D field, right? So now we're going to see if you can get this term in there as well. Let's see. Okay, for a conductor, we know that for an ohmic conductor, we know that this relation holds. So I'm going to insert this because then we can work only with the fields, and that's easier. So I insert, let's see. This is then equal to the, yeah, okay. So I get the time derivative of the d field in the frequency domain turns into the following: I omega d of k omega equals minus I omega epsilon of k omega e k omega. There's a lot of k omegas today. Sigma e. And this is the current, right? Using Ohm's law. That was long. Okay. Now I solve for d because I want to see what is d. And then I divide by I omega, and I get this term is the same. I drop the vector symbols if you don't mind. And also this conductivity term becomes I sigma over omega times E. Like this. Okay. Now we saw that before we took this part, right? And we said that, well, P is proportional to E, so you get out a constant times E. And now I'm doing the same because I have E here and E there, so I factor that factor out, and we get this on the same form. So it's essentially epsilon of k omega plus I sigma over omega of k omega E, like this. And now we see that it's on the same form as we had the electrostatic displacement function, except we have also a frequency-dependent term containing the conductivity. I stress that the conductivity itself is frequency-dependent in addition to the omega here. But you can see that this is explicitly frequency-dependent. Okay? And let's see. This means that we simply to go from then the case without conductivity, where we just had an epsilon, we go to the case where we have the polarizability of the material plus the sigma term, I sigma over omega. And now this is a complex epsilon. So you could call it perhaps epsilon tilde or something, depending on if you want to stress that it's complex. Anyway, you see that there's the polarizability and the conductivity as well baked into the dielectric function. And now we can use much of the machinery that we had before, except we now have the conductivity included as well. And an advantage of this formulation is that, for example, like we did last time, the few of us who were here, we looked at the Fresnel formulas. And now we can just insert this new complex epsilon right into the Fresnel formulas, and we get out the reflection and transmission amplitudes without resorting to complex wave numbers. But we'll see that as well, how you can do that. Okay. Now we remember that, yeah. How did I get to this first equation? Well, this term is important in Ampere's law, right? So this is interesting. This is more or less what defines the D field. So I'm going to take the Fourier transform of this to go to the frequency wave number domain, and then I get what's up there, right? And I also added Yeah, so we start out by Ampere's law. And then we have the current, right? And the time derivative of the d field. Okay? So what I'm doing here is essentially putting this into here. Okay? So I take the Fourier. So let's see. Let's call this dr for d real or something, and then I call the whole thing dt d complex. Okay. So I'm going to put this term into this guy here, so I can use it in Ampere's law or wherever d shows up. That's the idea. Okay, and if you remember when we derived the wave equation, we used Faraday's law. So I'm going to try to insert this into the Faraday law and see what we get out. Okay. So now we recall that we took the curl of the Faraday law to find the wave equation. So I'm going to do that. Curl of E is equal to minus dt curl of B. Okay, and the curl of B, well then I insert Ampere's law here. So we get minus dt, and yeah. And well, now I'm going to do this. Now I did it in the frequency wave number domain, but because you might not be so familiar with that, I'm going to do this in the time domain as well. So you get to see how it shows up here. But now we need to assume that epsilon and sigma are time independent. Right? Because we have time derivatives here. Now, this is not really true because they are frequency dependent, so they must somehow be time dependent as well. But we're not going to go into that because it's always easier to work in the frequency domain. So that's what people do. Let's see, so we get the time derivative of mu j. I get the mu now because I multiply by mu to get b in Ampere's law, right? And I get plus epsilon mu dt e, like this. And if I insert here Ohm's law again, I will get minus dt mu sigma e plus epsilon mu dt e, like this. Okay? Now I'm assuming that mu is a constant with respect to time, so I can just take it inside or outside the derivation as I want. And this gives me, well, if we still assume that there's no charge accumulation, then we remember that this is essentially nabla square of E, right? So we get the wave equation again. Except we, let's see, first I get this term, same as before. But I also get this term, which is new. So if you remember from some course in partial differential equations, then you see that this is a, if this term dominates, if I just take away this term, well then this is a wave equation, which you've seen before. And if I take away the wave term and say, okay, if the conductivity is really, really high, well then this term is going to dominate, and it's a diffusion equation. Okay, so depending on the balance of these terms, you could either have a wave-like behavior or a diffusive behavior. Okay. Okay, so for now, as always, we're going to assume a plane wave solution because we can then, by superposition, work with several waves if we need to do that. So let's see. And then see where this leads us. Well, let's see, the solution is E naught e to I k vector r vector minus I omega t. And if I insert this into star, then I will get the following. Now the double spatial derivative is going to give me k square. So I get, let's see, I square k square. That's this term here. And then this back out again. But this is going to be the same for all terms. I'm just going to take that away. And we get epsilon mu times the double time derivative, which is minus I omega square. Okay, and then the diffusion term, which will give me then mu sigma minus I omega. And the ones who are not falling asleep will notice that there's I square here and I square here, so I get rid of the I in the wave equation. But here I won't get rid of it. And so if I rearrange to have k on one side, the wave number, I get that this is equal to mu epsilon omega square. And I multiplied by minus 1, by the way, but I'm sure you noticed. Plus I mu sigma omega. And if I further rearrange this a bit, you'll see that I get out mu for both terms. And then epsilon plus I sigma over omega square. All right? That was okay? Now, well, what I got was exactly the same as in the frequency domain. Right? Now I had to assume frequency and time independence for epsilon and sigma. But you saw that in the frequency domain you got the same result, actually simpler. Now, this of course means that the k is complex. Because when I take the square root now, I'm taking the square root of something that has a real part and an imaginary part. So I'm not going to get the imaginary part away. So I have a complex wave number. And because of that, I will write k in the following way. K is equal to k1, which is simply the real part, and then I k2, which is then the imaginary part. And we can see what what the real and imaginary part are if we use the formula for the complex square root. Now let's see. The formula goes as follows. You have a plus ib under the square root is equal to, and then there's a plus minus, right? As always. And then you have half a square plus b square plus a plus I, almost the same, with a minus here. So now I can use this to take the square root. It's easier this way because I get out the Cartesian coordinates. And then we get k1 and k2. Okay, everyone is following? Let's see, k1. There's an omega, which is common for everything. And then we get epsilon mu by 2. And then 1 plus sigma over epsilon omega square plus 1 to 1/2. Okay, and the K2 is going to be very similar. There you go. So now we have the real part and the imaginary part. But what does this do to our solution, the plane wave solution? Well, now I can insert K into here, real and imaginary part separately, and we'll have a look at that. Okay, so the plane wave looks like the following. E naught constant, then e to I k r minus I omega t. And now I insert the real part and the imaginary part of this separately, and we get e naught e to minus k2 dot r. And this, of course, comes from the fact that we have k is equal to k1 plus I k2, and the i's join forces to create a minus sign. And then we have e to I k1 r minus I omega t. Right. So because k-term complex, gives us a wave that is attenuating as it propagates. So we see that when you have conductance, not surprisingly perhaps, the conductance actually takes energy out of the wave because of the ohmic losses. Okay, and just to stress that this is different from what we looked at before, where you have the evanescent waves at the interface. The case we had there was that you had an incident wave, k, and then if this medium has n, let's say n2 less than n1 up here, then you get total internal reflection, right? But we still have some electric field here, but there's no energy transport and there's no energy dissipation, because that's because the wave is reflected again. While here we have a wave traveling to a medium. So there's a conductor surrounding us everywhere, but as we propagate, the intensity of the wave drops because of the attenuation. Okay. So let's see the 1 over e depth. So if let's say you shine light on some metal perhaps, and then you have some field intensity here. Let's call it E of x1 equals 0. And then the depth d, where you have that E is equal to 1 over E times E of x1 equal to 0. That is, we have that the depth in the material is the same as the k. So you have e to minus 1. That's called the skin depth. So it tells us if we shine some sort of light, or radio waves, whatever, on a conductor, how far does it go into the medium before it's reduced by a factor 1 over e. And it's simply 1 over k2. Okay. Now I think you should go home and check your microwave oven, estimate how thick the walls are, try to figure out the skin depth at 2.45 gigahertz, which is the microwave frequency, and see if microwaves get out of your oven. And also you could try to estimate how much aluminum foil would you need to wrap your mobile phone in to silence it. So let's say if you want a mobile phone free room, you could put aluminum foil in all the walls. and see how much do you need. And in fact, it's quite little. So I think you could actually do it with paint. I heard someone who tried that. I haven't tried myself because I actually want to call people on my cell phone. But, okay. Did you have any questions on this, by the way? No? Okay. Just some notes on the magnetic field. Let's see. As in a vacuum, we have that H is K cross E over mu omega. And in a conductor, the K is complex, as we just saw. And this means that there's a complex phase here, right? Which is different on E and H. So there's going to be some sort of phase shift between the E field and the H field. So while in vacuum they were exactly in phase, they're no longer that. And the reason, of course, is, well, let's say, if we align E and H along the axis 1, 2, 3, so that we have E is equal to E x1 hat, H is equal to x2 hat H. This is just to get rid of all the vectors to make this a bit more clear. The physics is the same no matter what the coordinate system as always. And K in the x3 direction, well then you have that H2 E to I delta H, where delta is some sort of phase. This is a plane wave, right? But I add some phase because it could be some starting phase on the magnetic field. It's equal to K3 over mu omega. And now, as always, K is perpendicular to E. So the cross product doesn't contain anything more than just simple multiplication. You get some phi here, which is the complex phase of the wave number. And you get E1 E to I delta E. And now you see that phi is equal to delta E. No, wait. H minus delta E. Okay? So for physical reasons, the wave has to be attenuated, meaning that you're in the first quadrant, and then the magnetic field then lags behind the electric. And there's a nice illustration of how this looks in the book. But this is just from the fact that epsilon, and therefore the wave vector, is complex. Okay. Let's see. Yeah. So any questions on attenuation?
Why does E have to be delta H minus delta E?
Because this is the real part, or the amplitude. Yes. I write this on the amplitude phase form, which you know from just complex numbers. And so I put everything on this form, and then you have the amplitude and the phase of this. So this is the only, let's say, complex part. Yeah, so I just divide by this factor here, and then you get delta H minus delta E. That forms phi. Yep, that's it. Okay, and now back to the problem we discussed the last couple of lectures. The system where we had incoming wave. I call the vertical component alpha, and I call the parallel component k parallel. And we get something else, right? Q, P, if something goes through. And now alpha was the following. Alpha of k parallel is epsilon mu omega square over c square minus k parallel square. And now that epsilon is complex, alpha is also always complex. Right? Because we put the conductivity right into the epsilon. And now we have to choose the sign, as always, to make it to be in accordance with the boundary conditions. Because we saw that we had the exponential decay, right? If you pick the wrong sign here, you're going to have exponential increase instead. Same case as before, really, except now it's a bit more tricky. So you always have to be careful to choose the right branch of the square root that that gives you attenuation. And but everything else in our previous discussion holds, as long as we keep epsilon complex. And this means that reflectivity and so on changes. And I'm just going to sketch the dielectric reflectivity as a function of angle, as we saw last time. So if we have air on glass, and we have some incident wave vector, then we can figure out what is the coefficient of reflection and the coefficient of transmission and plot them. So if I just plot the reflectivity, it's going to look like this. Okay, so we get for S polarization something that goes like this. And for P polarization, you remember that we had the Brewster effect, meaning that you get something like this. All right, this is a dielectric. Glass is a dielectric. It has essentially no conductivity. So there's only a real part to the epsilon. Now for the metal, for example, or some other conductor, the figure changes slightly. So we have the reflectivity from some conducting surface, and it looks more like the following. The reflectivity is in general quite good for a conducting surface. The S polarization looks like this. And the P polarization looks like this. And while this is called the Brewster effect, which I'm sure you heard about before, this is called the pseudo-Brewster effect. And of course the difference is that epsilon doesn't quite, well, if you look at the Fresnel formulas, the numerator doesn't quite go to 0, because now epsilon is complex. So it's really hard to hit the 0 in a two-dimensional space, right? Because the complex number form a plane, while the real numbers form a line. So if you want to change signs on the real line, well, then you're going to have to go through 0, but in the complex plane you don't. So this leads to the Brewster effect. And the physics is, of course, that while in this case you have dipoles that don't oscillate in such a way that they don't radiate in the Brewster angle, while in this case you actually have charges that generate radiation in any angle because they're free to move. So here it's the dipoles. It's only dipoles, meaning that you get this Brewster effect angle, where the reflectivity just drops to a complete zero. While here, you also have the monopoles, the free charges that move around and create currents. That means you have always some contribution to the reflectivity. Any questions on that? Before we move on? So who can explain me the Brewster effect? The physics behind it? No one? You heard about it before? Yeah, okay. So a short digression into that. Right, so I have some interface here, and I shine light on it. Let's say I start off by S-polarized light. Meaning that the E field is perpendicular to the plane of incidence. Like this, and now when the light comes down to the surface, let's say this is vacuum, and this is some dielectric, let's say a glass surface, to take something familiar, then the electric field is oscillating like this, right, with respect to time and space. And when it hits the surface, it starts to polarize the material locally. So it starts shaking the electrons back and forth out of the plane of incidence, right? And so when a dipole radiates, let's see if you have plus Q, minus Q. So let's imagine that these oscillate. So this one goes down, this one goes up, and after a short amount of time, they're the opposite position. This sends out radiation in this direction, but not in this direction. I'm sure you remember that from when we calculated the electric field from a dipole. There's nothing in one of the direction because of there's a, I don't know, sine or cosine term there, which cancels out everything here. So when you shake this, the radiation goes here. There's some sort of angular distribution, so most of the radiation goes here, a little bit goes here, and nothing goes up here. But now they oscillate like this, so they radiate all over the place, right? Because this, let's say, angular dependence here is now, well, if you rotate it, it's everywhere here. Okay? While if we have parallel polarized light, so we have, let's see, like this, for example. Well, then there's the electric field is like this, so we start to oscillate the dipoles. Let's see, dipole moment is P. So we generate a time-dependent dipole moment oriented like this. So for one certain angle, where the angle of incidence is such that, let's say, the transmission angle here is 90 degrees to the angle where the radiation is going out. So this angle is equal to this angle, right? This and this. So when the transmission angle is just right, then the dipoles oscillate like this, and you don't see any radiation in this direction. This is sort of the microphysics behind the Brewster effect. So this means that for S polarization, this angular dependence just showers the whole plane of incidence, while here you get an angle where you always have some radiation going out. But if I turn on the conductivity, well, then I can start to shake electrons that are not bound, not just the bound electrons, the dipole moments, but I can just move charges around on the surface like this. And this will give me a reflection in any angle. So for metal, you have the dielectric contribution looks similar to this. No, sorry, the dielectric or polarization contribution looks like this, but which drops. But there's always some conductivity contribution, which lifts this up from the zero. Right. Does everyone know what the Brewster effect is now? Okay. That's good. And one of the last things we're going to go through in the course is, in fact, radiation from such dipoles that oscillate. So we're going to get this on a more mathematical footing, but this is the principle. So I think we just continue 10 past. Okay?